Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm happy to introduce Fan Yang. Fan's finishing his PhD at Cornell. His advisor is Johannes Gerke. And he's going to be talking about work he's done on how do you go about building, developing, optimizing web applications. So, Fan?
Thanks, everyone, for coming. I hope more is watching this online. Today, I'm going to talk about the work I've been doing on developing, optimizing, and hosting data-driven web applications. So in this talk, I will first summarize the problems of developing such applications using the current approaches. Then I will discuss our solution, which is a unified development platform based on a new language we designed called HILDA. So as we know, data-driven web applications are stateful applications that normally use a backend database to host and manage their application data persistently. Example of such applications include like popular online shopping site Amazon and online auction site like eBay, and also this course management system, which we will use as a running example throughout the talk. This system is normally used in school and allowing teachers and students to manage information related to the courses. The most implementation of such data-driven application follows the standard three-tier architecture. That is, you have a backend database server like SQL Server or MySQL that hosts your business data persistently. Then you have application server, which is like a WebLogic or WebSphere that hosts the application logic of your system. And such logic normally includes all types of code to like update, present, or manage your application data. And then at the front end, you have a web browser, graphical web browser like in your PDA or your laptop that allow users to interact with the system. The design of the three-tier architecture is mainly for the scalability for such applications. That is good, but exposing the details for three-tier architecture also expose great challenge for developers to develop such applications. First, because current solutions normally use different data models and programming languages to model the state and the application logic at each layer. For example, at the back end, you have entity relational models, entity relationship models, relational tables, or SQLs to manage your business data persistently. Then at the middle layer, you have some object-oriented programming language like Java or Ruby to develop application logic. And at the front end, you have like HTML, JavaScript, which are totally different programming language. The problem of using multiple languages to develop such applications, basically developers not only have to learn like more than one programming language and data model, they also have to write a lot of code to bridge the difference between each layer. For example, in J2EE, you need to write a lot of EJB configuration to just map relational tables into Java objects. And this caused this well-known problem called the impedance mismatch. And what's more, exposing the difference between multi-tiers to developers, forcing them to decide where to implement a particular functionality during the development time. For example, in the course management system, we can have a table showing the list of students' information. It can be sorted based on different columns according where the users click. To implement such functionality, you can either do an order by clause SQL in database systems, or you can sort in Java, reconstruct the web page and send it to the front end, or you can actually cache the data at the front end and use the JavaScript to do the sorting, which saves some round trip time and also give users better experience, if possible. But the decision, like which solution is the best, actually depends on runtime property of your system, and also the type of clients you're actually using to view the web pages. For example, if the table is very big, or you are using like a PDA to view the web page, probably a server-side solution is good, or otherwise, like a laptop client or small data size, probably pushing the operation and data to the client side is better. So as we can see, such decisions currently is made statically by developers. It not only increases the development time, also the current decision is not based on some quantitative criterion, like to improve the user's response time. They're mainly based on their personal experience. And also, as systems evolve, you may change the decision you just made. You may want to move some server implementation to a client side. That means you have to re-implement a large part of your application in a totally different language, and which is bad. And also, by pushing data and operations to the client side, you need to do a lot of complex logic, like maintaining the client server state consistency manually by the developers. And such practice actually is common, very normal in Web 2.0 applications. And you can see actually it's not very good. There's no really good solutions to do that. And besides that problems, there are many cases actually the non-technical users also want to build data-driven web applications. For example, in a social network setting, like in a Yahoo group, Yahoo group for book club reading. The group manager may want to have a web page that allow himself to publish the list of book reading events and allow other members to come in, maybe register themselves for the events or give feedbacks or give ratings for each event. And under current solutions, without the programming and the database schema design expertise, there's no way we can allow them to do that. And even if we can allow them to build such simple and small applications, imagine in a large social network settings, there can be tens of thousands of such applications. And providing a hosting backend platform would be very challenging in terms of scalability and the maintenance cost. So I have been, feel free to interrupt me if you have any questions. So I have been working on the solutions to deal with those problems. To solve the impedance mismatch and manually partitioning application logic across client and server, we proposed a new language called HILDA. HILDA is a declarative language for data-driven web applications. It is based on the relational models to capture the application state and the logic for the whole application stack. So it provides a unified programming model that allows users to just develop their application in this single language, and then the system during the runtime will generate the correct implementation that runs over the standard three-tier architecture. So this language basically hides details from the user and take the decision as what implementation to choose over by the system instead of the programmers. I've been also working other projects like at Yahoo Research, where we developed a WYSIWYG WYSIWYG development platform for non-technical users, where they just graphically specify the content and structure of web pages, and the system will automatically figure out what is the appropriate database schema and queries to generate to support those data-driven applications the user wants. And I also work on the hosting database platforms that is built on top of community hardware and software that is scalable to host tens of thousands small applications and provides multi-tenancy support for those applications. So we basically propose a method that we can co-host those applications with minimum hardware consumption while satisfying the service level agreement of each application. Question?
Any security guarantees in that, or is it more about scalability?
In this case, we do not consider much about the security part because this generates mostly the client server side solutions. So during this talk, I will focus on the first two problems I studied. That is, I will use the HILDA language. I will use the example of course management system to illustrate the high-level idea of this language. I won't focus much about the syntax details. So the course management system is developed at Cornell University to simplify the management of large courses. Currently, it's used by over 2,000 students. It was implemented PHP and then later in J2EE, which is the current running version. And we re-implemented the whole system using HILDA language to illustrate the strengths of this language. And to give you a simple idea about what you can do in the course management system, as a student, you can log in and view the list of courses you have enrolled in and select that course and then see the list of assignments in that course. And then for each course, you can send the invitation to or accept the invitation from other students to form a study group to work on that assignment together. The current approach like PHP and J2EE has several problems besides the impedance mismatch and also limited chances of optimization. They also tend to mix application logic with presentation. For example, you can easily write JavaScript code that controls both the structure and appearance of your web pages and also updates states and implement some application logic, which is especially hard when it comes to code reuse. For example, your PDA version of your website and your laptop version of website can look very differently because of the limitation of the screen size, but they can perform the same functionality. If you mix the application logic and the presentation in such a way, it's very difficult to reuse the code for application logic while changing the appearance for different versions. Also, web applications by their nature are distributed applications. Conflict can happen when you have outdated states at client side. For example, at the course management systems, you can have student A and student B log in. Student A send an invitation to student B to form a study group. Then student B log in and view the list of assignment it received, invitations it received. But before it tries to accept that invitation, student A withdraw that invitation. And then without refreshing the page, student B will see an outdated list of invitations. And then if it tries to accept that invitation, conflict will happen, and you need to deal with that. Otherwise, the system will be in an inconsistent state. Such problems, if it happens in a database systems, we can use transactions. But it's not the solution here. For example, in this case, you may want to make the view assignment list and accept assignment list, those two operations, as part of one transaction. And it can guard against such conflict. But the problem is the student B can just wait arbitrarily long period before it accepts that invitation or not accept the invitation at all. That will result in very long-running transaction and will potentially bring down the whole system. So the current systems, we are not equipped with models like transaction to deal with such conflict. So to solve all those problems, we proposed a language called HILDA, which stands for High-Level Declarative Language for Data-Driven Applications. It's designed specifically for data-driven application. It's not a it's a domain-specific language, not general-purpose programming language. And it's based on relational model to capture all the states of all layers in your application. It uses tables to model the backend database schemas, the runtime state of your application, and also the content as what to show in web pages. Everything is pushed into relational models, and that reduces the impedance mismatch problem. Also, it's declarative. It captures all the application logic in your data-driven application as state transitions and the table updates. Each state transition is specified as a set of condition action pairs, where condition is just a queries over the current state, and actions specify how you transform your state from current state to the next one. So before I give you more details of the language, I want to discuss a little bit about the related approach to address the same problem. So there have been a lot of work to deal with like impedance mismatch problem. It's a decade's effort to do that, to solve that problem. On one hand, we have like a generous purpose programming language like persistent C++ or like J2EE or like a Link, I think developed that here at Microsoft. The approach they are taking is they're trying to hide the relational tables inside their generous purpose programming language. They wrap tables as objects in the language like C++ or C#. The problem is it makes the language very complex and extremely hard to do sophisticated optimization automatically by the system. And on the other hand, on the other end, we have this.
Sorry, I don't understand that. You said it makes what complex? You said doing an object to relational mapping makes the language complex or the implementation complex?
The language itself basically is a generous.
You're just abstracting the database as a set of classes. Why is that complex? Isn't that the whole goal?
No, my objection to this approach is that the language itself is pretty complex. They are trying to propose the generous purpose programming languages that hide relational tables inside their language.
So you're saying object-oriented programming languages are complex?
Yes, like a persistent C++, they don't do some extensions, but the other approach like Link, they actually introduce the different construct just to manage relational tables, like queries inside their language.
So query, okay, I'm just lost as to what the source of the complexity is. Is it queries that...
Both parts. Basically, one part is language itself is complex. Doing automatic optimization over those languages is difficult. Second, by including the relational tables, which will increase the complexity of the language itself as well.
All right, maybe this is something to take offline.
Okay.
Actually, it's the first time I've ever heard people complain about object-oriented programming languages as a bad programming model for...
No, I'm not saying it's a bad programming language.
I thought it was widely believed to be the best model for accessing relational data, and the problem was in the implementation, not in the language interface. But apparently you feel differently about it, which is...
For the developers, it's natural, but not maybe it's okay, but not for the system. Yes, I agree part of your comments about the implementation part, and also as stated here, basically it's very hard to automatically optimize this language because the system do not understand much about the system. For example, in persistent C++, you write for loop to do the join. And the system cannot detect this for loop and convert it to a join in query in database.
But the link implementation just translates link into SQL, and then you run your SQL query optimizer.
Right, but you can't optimize it with other parts, like the optimization we will talk later.
Okay, I should probably wait to see what your alternative is.
Right, there's many opportunities. Right. Okay, yeah, it's a good point, and we can take offline or if I don't solve your problems later. So on one end, basically a lot of effort is trying to use a general purpose programming language to deal with the impedance mismatch. On the other side, we have declarative language like Strudel. I'm not sure if you heard about it. It's a declarative language that allows you, so you just write declarative queries to transform your database content into web sites, structures, web pages. The problem there is a very limited express power. It only generates like a read-only websites. They don't have application, the logic for updates. And the HILDA, the approach we're taking here is we're not trying to propose the generous purpose programming language. We're trying to find a sweet spot in the middle where it's declarative and simple enough so you can do all types of optimization. And on the other hand, expressive enough to capture most of the logic required in the data-driven web applications. Okay?
Why is read-only websites a key restriction?
Which part? You mean the Strudel?
Well, you mentioned that, right? The second bullet under Strudel.
Limited expressiveness power. Like the Strudel, this language, it's a declarative language for constructing websites from database. Basically, just the map relational tables into HTML and the web structures, but they don't capture the logic like updates, the user's interaction. Like I can submit a form that update tables, bring me to another page. They only do read-only. You can only. Does that solve a problem? Okay. Okay. So basically, the HILDA language is designed to solve those problems and trying to find a sweet spot in the middle. It is UML based, and it extends the UML programming paradigm with two basic constructs called A unit and P unit. A unit represents application unit. P unit means presentation unit. So A unit is analog to a class. It is used to model a functional component in your application, in your system. So you can consider A unit as a page or a subpage in your application. It captures the set of operations you can perform in that subpage, also the related business data for that subpage, and also the content as to what to show in that subpages. And the instance of A unit will be transformed into HTML pages by P unit. P unit is HTML template based. That's just a transform like tables into HTML pages. It contains no logic to update. There's no application logic there that allows you to update like table contents. And by separating the programs into A unit and P unit, we basically separate the presentation from application logic. And to give you more details about the application logic, the graph on the right side is a functional components graph in the course management system. It contains like a student side operations and the faculty side operations. And for students, you can view a list of assignments, maybe in the page. And you can do study group management, like send invitations, withdraw invitations. And each functional components in this graph will be captured by a unit programming construct in your language. And then forms the similar graph construct as the functional graph in CMS. So each A unit is a single input, single output construct. It can receive input, single entry, single exit construct. It received input from and it can also send output to its parent A unit. Each A unit contains two types of states, that is local and persistent states, where the local states captures the runtime state information during the application. For the application, it is like a local variable to the instance and is private to that instance. And the persistent states capture like the business data that should be kept in database persistently. It is shared among all instances of the A unit, of the same type of A unit. And both local state and persistent state are modeled as relational tables. It also contains the logic part. The activator basically controls like when and how to create children instances. It's a declarative query over the current state, like input, output, and local and persistent. This query basically tells us what children instance and how many of them to create, and also what input should be sent to the child instance. And output handlers basically contains the state transition logic. Whenever a child instance return output to its parent, the output handlers can be triggered if the condition is satisfied, and the actions will be performed to update the states like persistent local states, and can potentially also send output to this parent. All the logic like activators and output handlers, all of them are expressed as declarative queries and updates also over the relational tables. And now let's look at, so for example, as the student side of the course management system, you have a functional graph like this, and then the corresponding HILDA program will look like that, where each A unit models the logic corresponding to each component, functional component. It can capture the operations which can perform, what to show on that web pages, like what business data to keep for that subpage. And the leaf level A unit, as shown here, are special ones. They basically models the interactive element in your web pages, like a drop-down menu or a button you can click. And whenever a user performs some operations like select an item from a drop-down list, it will trigger that A unit instance to return output to its parent. And that which can potentially update the logic, update the states in its parent. If you are totally confused here, don't worry. I will use the running examples to illustrate the idea here. So let's see what happened during the runtime. So let's say a student now log in, and the system start executing by create an instance of the root level A unit. Question?
You also can capture the login logic, basically, the protocol between
right.
client, server, and different states, etc.
Yes, well, I'll skip that part because it's all too tedious, but you can still model that as like a state transition as well. For example, a login means you add your information into this current user tables.
So you view this kind of protocol as a single state machine type of thing that describes both what happened at the two ends, the client side and the server side? So you view the protocol logic as a single state machine type of thing.
It is a single state machine, right. It's maybe a unit called login. It has the leaf level A unit, maybe an input field. Whenever you input something, that A unit will get your login information, check against the table storing the password and the username. If it succeeds, it will go through. The current login table can be updated by this new login user. But this is a semantic model. It doesn't matter whether it's in the client or server side. This is beyond this semantic model. This logic can be implemented or kept at the client side or the server side. The developer don't need to worry about that.
But you need to project at the implementation level when you compile. You need to compile code, so to speak.
That is automatically.
So there has to be a hint from the programmer using the language to say this might happen on the client side, this might happen on the server side, right?
Well, in our case, we try to reduce the hint from the developers as much as possible. So basically, some information like kept persistently as in database, then this logic is kept at the server side. Otherwise, they are free to distribute this either on the client or on the server.
But how do you deal with the issue that the tier side currently, that they currently have different trust levels?
The security concerns for partitioning the logic across client and server is something we will study. Currently, we only look at the performance aspects as to how to partition your logic across client and server. And I think there's a lot of work on the security side as well, using some information flow and developers' annotations like that. It can be included in our programming model. Maybe just annotate this A unit has to maintain at the server side. But currently, we don't have that part. Okay, so during the runtime, basically, the system will just create instances of A unit, and it will start by creating a root level A unit when a user session begins. And it will continue, and this A unit contains like the persistent state, which are like student tables, course tables kept persistently at relational database, and some local runtime state, like what is the currently login user, and what's the selection as to which course to view, initially is empty. So based on the current state kept in relational tables, the root level A unit will just continue to activate instances of its child. And the root level has two child A unit. One is student course and one is navigation bar. Since the student do not make any selections right now, then no student course instance will be activated. It will only activate the instance for navigation bar. And the input is specified as a declarative query. The syntax here isn't that important. It just says the input for navigation bar would be the list of courses that the current students enrolled in. And then no more instance can be activated. Now the instance tree reaches a stable stage. Then the presentation unit will map this instance tree to the corresponding web page. So the course management system basically corresponds to the whole page, and the navigation bar corresponds to the area on the top. And whenever a user perform some operations in this navigation bar, say select a course, that will trigger the leaf level A unit, which is navigation bar A unit, to return output, which is user selection, to its parent. And that returning from his child will trigger the output handler at the root level, which will update the local state in this case. And in that semantics basically just says the current state of selection table depends on the user's selection. And now the states of applications is updated. The instance tree will be refreshed based on the up-to-date state. So in this case, new instance of student course A unit will be activated because the selection table is updated. Again, this is the activator query. The semantic syntax details is not that important. Basically, it just says for each course the student has selected, we activate an instance of student course in the activation tree. And this A unit will continue to activate instances of its children. And in this case, we will activate an instance of a view assignment list and also another navigation bar. And this view assignment list A unit will activate a row A unit instance for each assignment in your list. And then the activation tree comes to another stable stage. And then the presentation unit will render this instance tree. We will refresh the web pages based on the new instance tree, which brings you to another page. And this area basically corresponds to the view assignment list. This area corresponds to the navigation bar. And each row here corresponds to one assignment in this subpage. And you can just continue this process by like a select assignment, which will trigger this one to return, and the whole instance tree be refreshed based on the new updated state, and then bring you to a new page. So basically, you can see how this HILDA language models everything, all the states as relational tables, all the logic as state transitions, and when state gets updated, the instance tree gets transformed from one tree to another, which brings you from one page to another page. This is basically the semantic model of the language.
Just a clarification. So in this example, execution was happening on the client?
This is the semantic model of your language. Whether it's on the client or server doesn't matter.
Well, but it also presumes that the runtime capabilities is on the client that
Yeah,
allow
exactly.
to do all of that complex
Yes.
stuff.
So that's the whole point of declarative language, right? Without the smart runtime optimization system, why do you need a declarative language?
Well, I'm sure you'll get into that.
Right. Okay, so yeah, exactly. I'm glad you bring it up because I want to clarify that this semantic model, this model is semantic. And the semantic, every time you update some, at the end of each state transition, like you reconstruct the activation tree, all the models are actually it's separated from implementation. You can perform all kinds of optimization there. For example, we have input and output, and if you have input and output which can be passed along the path of your instance tree, instead of copying the data away or around, you can just pass the input-output as view definitions instead of materializing the data during the copying. Only when you use it, you include that as part of your query. And also, even the older states, like a runtime state, are captured as tables, but not all the tables are really kept in the database. Some of them just kept in memory. You keep a memory structure of them. And although all the state transactions are specified as declarative SQL queries, some of them are not implemented, not issued to the database. You basically do that in your runtime system. And also, like semantically, you refresh the whole tree every time after each state transition. But we can smartly just refresh part of it because the states update some tables, and then some instance depends on that updated tables, where some don't. For example, you select some assignment to view, that won't change the navigation bar part. And that part of the web page will not be refreshed. And such optimization is important to implement partial update to your web pages which you have to write a lot of code currently to develop partial updates semantics in your Web 2.0 application. And in our case, that's all managed by the runtime system. And also, this activation instance tree is maintained whether on the client or the server, or part on the client, part on the server. It's really our runtime system's decision. Okay, any question? Further questions? Okay, then let's see what's happening when you have multiple users log into the system. So you have a student A and a student B. Semantically, each instance tree will be maintained for each user session. And when student A, say, click the button or fill in an invitation, send an invitation to student B, that will trigger this leaf level unit instance to return, which propagate the information all the way up and update the persistent table on the root, which keeps all the invitations in your system. And since this persistent information is shared across all the instances of that course management system A unit, semantically it will refresh all the instance tree. So after A send invitation, accept invitation A unit is activated for student B, and this withdraw invitation is activated for student A, and their corresponding, and the activation is controlled by the activator. Question?
Walk through that again. So you said, I understand that the send invitation is now propagated up the tree and stored in the database.
Right.
Now what happens? I mean, is there a trigger in the database, or I mean, what is it that causes the information to flow down the other side?
The semantic model is every time the state is updated, all the instance tree will be refreshed based on the new state. So semantically, if you change anything on the database, that means all the clients will receive that updates. All the users will receive that updates. Their instance tree should be refreshed based on the new table.
That's pretty eager. I mean, in a web environment, this sounds like something that might not scale very well.
This is semantic model, right? You can do it. It's a real implementation. Lazily refresh the tree for each users. So only when student B performs some operation that triggered its browsers to contact the server to refresh its page, this reconstruction of the instance tree will be triggered.
But does that violate the semantics of the language? I mean, you just said that when you update the state, then all the trees are conceptually...
Well, the semantic is the instance tree should reflect the most up-to-date state. It doesn't matter, it skips some state transition in the middle, as long as you can reach the end. So the instance tree is solely based on the current state of your application. Maybe we can take... Maybe we can...
It's a minor point, I guess, but...
Okay, maybe we can take this offline later.
I think I would tend to agree with Phil. I think this super eager update is kind of unnatural in these environments. I think conflict detection happens at the time of a commit of some sort, of zero crossing usually. If you have an application, you're typing something, and then there's an updated comp sensor that messes with your current typing in some sense. That's not the best experience, perhaps.
Well, this semantic model is done this way. It's just to say, if student B is very eagerly to refresh the page, it will always receive the most up-to-date information. Right? If it's not eagerly refresh its page, it's okay, I skip something in the middle, and only when it's contact the server, I give it to update information.
We'll talk about that.
Okay. So now what happened if student A, say, withdraw an invitation, which will just get rid of that line in the persistent tables, then both activation tree will be refreshed, and this accept invitation will just disappear, that instance. And what if the student B didn't refresh the page and still see that button? The system can detect the conflict by knowing that the operation comes from a unit instances which is no longer there. and it detects the conflicts based on that rule. Okay, and so the semantic model here basically says operations received. So the semantic model is it makes the state transition as an atomic operation, and it's as if the operations received from all the clients are serialized in some order, are sequential in some order. If student A and student B perform the operation at the same time, the system will serialize, schedule them one after another. Any question about that part?
Does it just drop that quick? I mean, in some sense, does it just say, well, this could never have happened, so I'm just going to pretend it didn't happen?
In this case, it's like a throw an exception. And the system basically detects, well, this operation isn't allowed in the current web page.
What's the user experience?
User's experience, you can, you need to write like a code or write. You need to include the semantics here to see what happened, whether you give you an arrow link, arrow page, or so that part is the same as the rest. Basically, when you do something relevant, you can come to another page, or you just refresh the current page saying there's a problem.
So where does that cleanup logic live? Is that part of your presentation layer, or because it's sort of strange, the user's just using this and they think it's perfectly fine, and suddenly they get, sorry, the object of your click no longer exists.
So in that case, basically, the system will just as if it's a return. So normally, if you accept invitation, it will receive this group management part will receive the normal output from that accept button. Right? Now, if you're clicking a button, if you're clicking on it and no longer exists, we will still send a message. So the group management part will be notified this arrow, and it will just trigger some output handlers there based on this notification saying something is wrong. It depends on your logic to say bring to a new page, explaining the problems, or just ignore that.
The next question, I guess, would be, is the group management code refreshed before it receives that message to the latest tree, or is the
Yes, semantically, basically, it's as if I perform the withdraw invitation first and then accept invitation later. In that case, when I try to accept this activation tree should be refreshed based on the state after the withdraw invitation.
The error is always detected sort of at the most local place possible.
Right. It's like a sequential model for the developers. It's as if all the operations come sequentially, and each operation, like state transition, is atomic.
So this error handling or exception handling mechanism is part of HILDA.
Yes.
Okay.
You can think of it as just a page navigation from the current page to another page. That page means arrow. Okay, so that is the semantic model of the HILDA language. Basically, we build on top of relational tables and add programming construct called A-unit and P-unit to allow us to develop applications on relational tables. And let's give you some current status of the system. Basically, we developed it actually is not a compiler. It's actually a preprocessor, because the language itself is interpreted at the runtime. And we have that HILDA preprocessor and the runtime system available as open source. And we developed a plugin for Eclipse and a debug platform allowing users to see this instance tree corresponding to each page, and when you do something, what happened to that instance tree graphically in the browser. Just help them to use the language. The course management system is re-implemented in the HILDA language, and compared to the J2EE and EJB JavaScript version, it's actually, we can see it only result in 1/10 of the length in terms of the length of the code. Question?
What are the absolute values?
Absolute values. This is like a about 10,000, where the other one is like 100,000. Right. Course management system is really complex. I only show a very small part of it. You can do some scheduling part, or yeah, it's
So you're saying that the amount of generated code is 100,000, not to say that somebody couldn't implement a shorter version of the
yeah.
limit.
So this is only anecdotal data. It's not really in a controlled environment. This course management system is developed by some other developers at Cornell. We don't have control over that. I assume they're smart people. Question?
Did you handle all the exceptional cases, all the conflicts?
Connect?
No, when you implemented, did you actually think of all the conflicts and implement the exceptional cases?
Oh, well, as long as it's handled in the J2EE version, we kind of do a apple-to-apple comparison there. Okay, and then so this for some people, such state transition, relational tables, SQLs can be difficult to use. Not everyone like it, and to just test whether it can be understood by the audience we are targeting at, we actually make this HILDA as assignment to a course we were teaching at Cornell. This course is for master students, and we taught them SQLs and J2EE web application development in that course. And we make HILDA as one assignment. We give them 2 weeks to implement a TA appointment management model in the module in the CMS systems. The 2 weeks, including the couple of lectures we give them to give them more details of the language, and also the implementation time. So the result is pretty good. All of them succeeded in finishing the job within 2 weeks. Question?
CMS and HILDA. So did you write that, and how long did it take you?
Oh, I wrote the HILDA language. It's I didn't really count because it's not in control environment. I just implement this part, and then later that part, like half a semester, not half a semester, like 1 month, 1.5 months. This time actually isn't really comparable to the time they spent on J2EE, because they also study like use case, what design, what functionality to include. Well, we just copy that part. Okay, so any question? No? Okay, so in summary, basically this HILDA language is designed for data-driven applications. And the philosophy is we try to make it simple and declarative based on relational models. So we reduce the impedance match problem, and also it opens up all the possibilities for sophisticated optimizations, among other benefits we provide. So let's look at the one particular optimization we can do on the HILDA language. Remember, the manual partitioning of application logic across client and server can not only result in increased development time, but also suboptimal design decisions for your systems. And let's look at another example in the course management system, where the professors can edit the list of stuff in the course. It can add like a TAs, remove TAs, and change the type of properties of each of them, and maybe sorting each list based on different columns. And all the operations that are local, only when it's click set or submit, the changes will be reflected on the database. And if you use, consider what you can do to implement this functionality using the current system. You need to write a lot of you can push this stuff list editing functionality to the client by implementing it in JavaScript. So when you remove row or add a new row or do the sorting, those operations only happen locally in the client without contacting the server. And only when you click submit, the information is sent over to the server side. But in HILDA, this implementation, we don't need to deal with that details, because so in the current Web 2.0, that is one way to implement that by caching this functionality and data in the client side. And in the cases like PDA version of your website, maybe a server-side solution would be better. And the current solutions, you have to re-implement it in a different way. But in HILDA, we only have one program. We basically have only one specification like this, where the stuff list corresponds to the area for that part. And this really depends on the runtime systems to choose what implementation to use during the runtime. For example, when the Professor A log in to the system with the PDA client, the server can smartly choose to maintain all the instance tree at the server side. And if the Professor B log in with the laptop, it can actually push maintaining part of the AUnit instance at the client side. Say by pushing the stuff list to the client, the local operations don't need to contact the server. And when you have like updates of the web pages, like you change the stuff list, other parts like navigation bar 1 or bar 2 don't need to be touched, which implements the partial update of the web pages that is very, very desirable in the Web 2.0 application. Any question?
So you had this explicit button set to make the updates permanent on the database.
Right.
Is that independent from whether you post it on the server or not? So I assume that in the PDA case, even though it's all hosted on the server, it still doesn't go into the database until I click set.
Right. So that is part of the application logic.
Right, and that is not changed, right?
Yes, that part is not changed. Exactly. The logic is still the same, while the implementation can be different. So all this is happened by maintained by this multi-tier runtime system we implement. This runtime system basically contains the client side and the server side. They coordinate with each other to implement the instance tree semantic of the HILDA language, the semantic model we just discussed. It hides the multi-tier details from the developers. So for them, they just manage the transformation from one instance tree to another without really worrying about which part is on the client, which part is on the server. And when the data is, or the operation, like instance, is kept at the server side, at the client side, the runtime system automatically maintains the consistency between client and server state. And the problem of maintaining the transactional client-server cache is well studied in the database literature. We currently only just implement the optimistic detection-based approach, while other approach to ensure the consistency can be seamlessly integrated into the system. We also implement some other optimizations besides the ones we just talked about. For example, when the server sends data to the client, we cache the data at the server side. So next time we only send delta information for the updates instead of sending over all the information again. Another task performed by the multi-tier application is it keeps the statistics about each AUnit instance. It keeps how much time you spend on it and what's the memory consumptions, which will be used later as the performance metrics to partition your instance tree into client-server side. And give you more details about this runtime systems. Now the server side is implemented as a Java servlet with connection to the database, and the client side is implemented as a sticky applet, which only the first time you connect to the server, this applet is transmitted over, and the next time you connect to the same site, you just fetch this runtime system from your disk in your client. And this is just one way we can implement runtime system on client side. You can imagine we use like JavaScript, Flash, all types of things. So the runtime system basically applied a quantitative methods for a partitioning application logic across client and server side. The metrics we are using is trying to improve the average user's response time over a certain workload. And also with the constraint at the client-side memory at mind. So different clients like PDA and desktop can have different memory constraint, which will result in different placement strategy for your instance tree. So during the runtime system will collect. So for under a certain placement strategy for your instance tree, we collect information about like how long you spend at each instance to do like state transitions, and also what's the memory consumptions for each instance, like what's the size of the local table states, and also the number of communications between each link in your instance tree, and also the size of the data exchange among each parent-child link. And under a particular, so during the runtime, basically we measure this information periodically by randomly sample the current workload of like all n users interaction. And we calculate the time, the average response time, as the time you spend on the client side, time you spend on the server side, and the time you spend by transmitting data. We sum it up and divide it by the number of users interaction. That is the average user's response time. So we are doing the optimization over a set of operations instead of each individual one, because this placement strategy can be different for different operation. We don't want to be too sensitive to the current operation and result in like a churning of your system. We are doing it over a set of operation. That's the reason. And to give more details about the cost model, say if in certain case we can only measure the time you spend on the server or the time you spend on the client, because when you're measuring this, it's under a certain placement strategy. It's either on the client or on the server. So you measure the time spent on one side and use the alpha parameter to estimate what would happen if I move it over to the other side. And the time you spend on dealing with data, including several components. One is the time you spend on materializing the data sent over the client-server edge, the transmission time of that, the amount of data between each edge, and also the connection establishment time. We're separating those two parts because in a typical web workload, the amount of data transmitted is very small. In the TCP protocols, you cannot ignore. Basically, when the amount of data transmitted is very small, you cannot ignore the time, the initial handshake, the initial round trip time to establish the connection. Any question here? So basically, the problem can be modeled as an optimization problem, which we just try to find the best placement strategy C that minimize the average response time over a workload. And also under the constraint that the amount of memory consumed at the client side should be smaller than a constraint on that on particular client. And this can be modeled as an integer programming problem. Itself is NP-hard, and we basically provide approximation solutions with the approximation bound of 3. And this actually is a theoretical worst case bound, and in practice, actually the result of our approximation algorithm is very close to the optimal one. We have set up a.
So you periodically sample and measure this, and so
yes.
you kind of move things around dynamically then?
Yes. Well, if needed. Basically, so the placement strategy we think is very sensitive to the type of operations the user perform. If they don't do any sort, then probably pushing this whole table to the client isn't beneficial at all. So we are basically learning from the historical experience. We periodically collect information of the workload, say for the previous 10 minutes, and then recalculate it every 10 minutes and moving things around if necessary.
So do you also account for the cost of moving things around in your model, or?
Well, that is part of the data transmission. You basically take the code transmission as well. You don't push the whole HILDA program to the client side.
What is a free approximation solution?
This is basically transform this integer programming into a linear programming model. Basically give each node as a parameter like x. As if it's 0, then it's on client side, 1 is on the server side. Model that's the integer programming problems, but the integer programming is NP complete. And we basically solve it as linear programming. And for each value x, we round it to either 0 or 1 based on a matrix. That part actually is, I think this solution is kind of not very new. It's kind of standard in the optimization literature.
Every NP hard problem has a free approximation. Can be reduced to this. You can perform this free approximation thing.
That is specific. This is something specific of this problem during the proof that give us this free approximation. In general, linear programming is not true that you can transform linear programming into. You can transform integer programming into linear programming with a given bound.
So, as a programmer, whenever I'm trying to cross a network, I have to think about various fault conditions, like the network can be disconnected. And so, what's a programming model from the user? So there can be a network from any two boxes in your diagram.
Basically, in our approach, we kind of hide all the complexity of when your clients go offline, what happens there. Is that your question? Basically, I need to deal with the logic, like the exception when problems happens that I cannot connect to the server side. Well, in our case, if your client goes offline, you can still perform local operations. But whenever it's trying to go across the network, the system basically will report error. That's kind of like a simple exception strategy we expose to developers. We don't really allow them to add more fancy logic there. Does that answer your question? Okay, and actually, I forgot to point out that our data-driven application, you can see we're trying to model everything as state transitions, but it's good for data-centric logic. Sometimes you have some computing-centric logic, like construct maybe a shortest path in a graph, which is hard to express as SQL queries. Then in that case, we provide external hook that allow you to wrap your logic inside an application unit. As long as you wrap it inside a single in, single out model, you can plug that into our instance tree model. Okay, so we have some perform some experiments to evaluate our runtime system and the effectiveness of our partitioning algorithm strategy. So we compared HILDA versus J2EE implementation for the course management system and also the online bookstore application based on the TPCW benchmark. The course management system is developed by some developers and is manually optimized in many cases. They include extensive JavaScript code to do the partial updating of your web page. And we deploy the client. We deploy the client simulator in the Planet Lab, which is a test bed for distributed applications that mimic the real network condition for the internet. And we use the workload, both real workload and synthetic workload. For the CMS, we have the trace of users' actions for one semester, and we just use that as to simulate the real case. And for the TCPW, we use the synthetic workload specified in the benchmark. And we have some results. Here, we basically compare the J2EE version and the HILDA server-only version, and also the HILDA with automatic client-server partitioning enabled. And in both cases, and in the first case, the average response time, the J2EE and HILDA is very close. and with slightly improvement. That means we can, well, this shows basically is the automatic optimization is as good as or even better than the manual optimization performed. And in the bookstore application, we can see a huge improvement with the optimization enabled over the naive implementation. What?
Is that because the code written in J2EE was not hand optimized in this case?
In that case, yeah. We just use the we just use the version that is available to the public according to this TPCW benchmark.
Who wrote that?
Each one of them has their own implementation, but it's not public. This one we use this from this NYU, New York University. They independently evaluate like a MySQL plus JBoss, and they have their Java implementation for the TPCW, make it open source and available to the others. We just compared with that one.
Could you compare the ultimate cluster distribution between, say, the J2EE case over there and the HILDA case?
You mean break them into operations? Or
can you give a rough sense of how they're different, I guess?
So we also break them into different operations. And for each operation, we measure the average. So one drawback of the current experiments is we only look at the average. We don't look at the variance, like what if happened. So we don't measure the stability of the system. Like when you recompute things, someone can get bad result, while others can get good one. That is ongoing work to compare the variance of each operation. And but breaking them into operations, we can see for the course management systems, we actually identified many chances for optimization that is missed by manually partitioning.
So what's going on in operation 6 in TPCW? Because that seems to be the only big difference between the...
Oh, there's a lot of difference here. Basically, it's the
6 and 7, I guess.
6 and 7. That is the partial updates part. Like if you add a new book in your inventory list, well, the other one is basically refresh the whole page. Well, our system basically just send it over. Question? Without refreshing the whole page.
So can you compare the partitioning that HILDA automatically came up with to the partitioning that is in J2EE?
Right. So the partitioning basically mainly from the benefits basically mainly from the partial updates of web pages. And that's most optimization done in a Web 2.0 application. You just use asynchronously, like contact the server and dynamically change the current web page without reloading the whole web pages. And you need to manually do that currently in our CMS implementation. And in our system, we kind of detect more chances that you can partially update web page and have it done automatically by the runtime system.
So in this case, for these two cases where you're much faster, basically they didn't do that optimization in the J2EE.
Right.
But did they, in the first case, in the CMS case, were they doing partial updates as well?
They are doing a lot of partial updates.
So they're just missing some.
They're missing some, also get some part wrong. Like very huge tables, they kind of tend to embed the JavaScript sorting code in your web page, which the loading of the web page is so slow as well, because the JavaScript code is very big, and they don't do some fancy things like partially load JavaScript code, which I think is ongoing research area in Microsoft Research. Okay. Okay, and in summary, basically, we are very compatible or even outperformed the manually tuned J2EE implementation. And okay, and then there's many related work in the area like persistent C++, like Link, and also other language designed for developing web applications. The problem is none of them is really doing the type of optimization or have this optimization built in, like the whole design of the purpose of the language, trying to optimize it automatically. And none of the current approach is following that direction. And there's also other work on mobile code that automatically decentralize application into a distributed setting. And there are many problems there as well. For example, they're not designed for data-driven web applications. To deal with like a data consistency across client and servers, they have to include a lot of manual annotations, which becomes another domain-specific language. While in our case, we're trying to keep everything simple and declarative and do the optimizations with very few manual intervention. So in conclusion, basically, you can see the big difference between our approach and the currently one. The philosophy of our system is basically focused on the declarative aspects of the system and opens the chances for optimization. And we have implemented some optimizations. There is actually a lot of more opportunities we can pursue along this direction. And besides this HILDA work, I have also been working on the XML query processing. We have a demo published in SIG-Mode and the full paper in VRDB. And this WYSIWYG development platform for non-technical users, we also have some demos and papers for submission. And there's a lot of future work we can, different directions we can pursue. For example, one big thing is we can consider security concerns, take security concerns into consideration while we partition code across client and server. The current approach mostly use basically annotations based on the user's input. And if we can automatically do that or infer some rules based on the declarative model, that will be an open question. And also we can do, now all the optimization is focused on a single application unit. The most optimization is related to where to place it, whether client or server. Actually, we can think about some other chances of optimization that is across a unit. For example, in your web page, you may, on one side, like in one part of the page, you show maybe the list of student names. On the other side, you can show maybe a graph of the students' grades. If the programmers now use different queries to retrieve the data for both of them, then currently we can't optimize that. But actually, you can think of merging those two queries into one big one. So you can find one query that returns both the student name and the query name to reduce the number of queries executed. And I think such things can be done over some information flow analysis. And that's definitely one interesting aspect we're trying to follow. And also the effect of like an online application. So our model is not restricted to online applications. You can think of offline application developed using HILDA as well, and how to we can pursue along that direction to blur maybe the difference between online and offline application. And also some other work in this effort is the WYSIWYG development form for non-technical users. We are trying to extend it, so capture more logic for non-technical users, allow them to build some mashup sites, allow them to integrate different data sources like RSS feed, and also build some intuitive or graphical interface allowing them to build more rich, more applications with more logic and rich workflow. So that's all I'm going to talk about today. Any question for me? Thank you.